we've been speaking about for the last few days, we've been speaking about firstly generating sets, then we spoke about linear independence, and yesterday we put these two things together and we started speaking about bases of vector spaces or bases of subspaces. And these are simply generating sets for that vector space or generating sets for that subspace that are also linearly independent sets. So that's what we've been speaking about. What we're going to speak about today is the idea of a dimension, and the idea of a dimension is going to follow very naturally from this idea of a basis that we've introduced. And then what we'll start tomorrow is chapter 2. We'll start speaking about the determinant, which turns out to be a really useful tool for a number of different things. So let's just start with what I'm going to call fact 1.18, which I think I may have said yesterday, but didn't actually write down formally. And fact 1.18 basically just says that if you have a vector space V, all of the different bases for that vector space V have the same number of elements in it. And we can say a similar thing for subspaces. If you've got a subspace S, all of the different bases for that subspace S have the same number of elements. And we spoke a little bit about this in the case where we had, R2, and we said all the bases of R2 are going to have exactly two vectors in it. If you only have one vector in the set, then there's no way that it can generate all of R2. If you've got three vectors in the set, there's no way that these three vectors can all be linearly independent. So R2 has got exactly two elements, and this is something which is true not just for R2, it's for all vector spaces. Although we're not going to show that this is true. It's actually fairly tricky to show that this is true. We'll show, I guess, later on in this lecture some part of it in some sense, but actually showing that this is true is quite hard. We're not going to do it. The remark which I was going to make, I'm actually not going to write this down, but let me just say what I was going to say, is that this is all fine and well when you've got finite bases, right? If you've got something like R2, which has got two vectors in it, or you've got R7, which has got 7 vectors in it. But when you start thinking about the space of all the functions from the reals to the reals, it's not clear how you would build a basis for that vector space. It's not clear how many elements would be, how many vectors you need in that base, how many elements it would have. And things start becoming much, much more complicated for what would be called infinite dimensional vector spaces. But we're not going to worry about infinite dimensional vector spaces. We're really mostly going to focus, when it comes to basis and dimension, on finite dimensional vector spaces, where we've got bases which have a nice round number of elements in them, like 7 or 5 or 2 or 1. We won't worry about infinities. Okay. But these two facts here motivate the following definition for the dimension of a space. So the dimension of a vector space or of a subspace, I guess we can just say the dimension of a space is the number of elements the dimension of a space is the number of elements in any of its bases. Or maybe in all of its bases. No, then it sounds like you're adding it up. Let's leave it as any of its bases. In any of its bases. So R2 has got a basis with two vectors in it, so R2 is two-dimensional. R3 has got a canonical basis. We wrote it down yesterday with 3 elements in it. R3 is three-dimensional. This is what we mean when we speak about the dimension of a space. So let's take a look at some examples, and you'll do most of the calculations today. Here's the first example. I'd like you to calculate the dimension of the following subspace. What is the dimension What is the dimension of the subspace of all polynomials of degree 2 or less? should be a question mark. Okay. And you can have a couple of minutes to think about this. What is the dimension of the subspace of all polynomials of degree 2 or less? So what you need to do is you've got to write down a basis for the subspace of all polynomials of degree 2 or less. And once you've written down what you think might be a basis, you should check that it is actually a basis. You should check that it is a set which is linearly independent. You should check that it is a set which generates all the polynomials of degree 2 or less and doesn't generate anything else. And then you just count down how many things are in that basis, right? That's all you've got to do. So you've got 5 minutes, let's say, to, we'll make it 4 minutes until 08:010. from what I can see, the people who had written things down had mostly written down correct things. Okay, so it seems like a lot of people tried the following. We consider it's called B because we want to show that this is a basis. We consider something like this. X squared, x1. We've already actually shown that this is linearly independent. I think we did it a few days ago. I'm not going to go through all the details again, but B is linearly I think that was about 2 days ago. So we know that this is linearly independent. And then the second thing we've got to write down is what B generates. So the set which is generated by B is a set, it's just all possible linear combinations of the vectors, in this case the functions inside B. So that's alpha x squared plus beta x plus gamma, alpha, beta, gamma, all real numbers. And we might recognize that. I mean, it's pretty clear that the things that we are generating over here are polynomials of degree 2 or less, right? It's 2 or less because we might set alpha is equal to 0 and then we get a first degree polynomial, and if we set alpha and beta equal to 0, we get a 0th degree polynomial. So we seem very happy here that this over here, let's say, is polynomials, rather, let's say, set of all polynomials degree 2 or less. So we've shown that it's linearly independent. We've shown that it generates what we wanted it to generate. So we conclude here, maybe one last line over here at the bottom, we'll say something like, therefore B is a basis. And I'm just writing down B is a basis. What I really mean, I suppose, is actually B is a basis for the set of all polynomials of degree 2 or less. Right? You should really always specify what it is a basis for. You can't just say, oh, this is a basis. It's always a basis for something. Is everyone happy with what we've done here? Yeah. Okay. So let's take a look at another example. And again, you can take a couple of minutes to do this.
Sorry.
Yes. Oh, sure. Yes, sorry. We didn't make a conclusion. Yeah, it wasn't just that we had to find a basis, we had to find the dimension. Okay, B is a basis for the set P2, therefore. So P2 has dimension 3. Yeah, okay, very important. We weren't just asked to calculate a basis, we were asked to find the dimension. All right. Yes? Okay, so the question is, why did we have to show that this was a basis? The question didn't say anything up there explicitly about a basis, right? But the question did say something about the dimension. And whenever we see dimension, we know that, well, let's just take a look at how dimension is defined, right? The dimension of a space is the number of elements in any of its bases. So we weren't explicitly asked to show that this is a basis, but we can only speak about dimension by counting the number of elements in a basis. So that's why we've shown that this is a basis. We've shown that this is a basis, B, then you count up how many elements it has, 1, 2, 3, so it's a 3-dimensional space. Yeah? Does it mean that P2 is in 3D? Yes, this is it's a strange way to think about things, but yes, right? So we don't really have a good way of visualizing the space of all functions from the real numbers into the real numbers. I mean, this is a complicated space. But we do have a nice way of visualizing R3. Now, one thing we could do to visualize this subspace here, because this is also a three-dimensional subspace, we've just done that this is a three-dimensional subspace, you could imagine a set of axes, and on the one axis is x squared, and on the other axis is x, and on the other axis is a constant, right? And so now a vector in this space corresponds to a polynomial. So the vector 1, 3, 5 corresponds to x squared plus 3x plus 5. So in some sense, R3 and the space of all polynomials of degree 2 or less are the same. The technical term is that there's an isomorphism between the two of them. Isomorphism, just the Greek root means the same shape. So yes, I mean, polynomials of degree 2, in some ways, this subspace here is exactly the same as the vector space R3. We were not going to show that, but yes, that is one way of thinking about it. Was there a question here? Yes? How do you know that this is the simplest basis? How do you know that this is the simplest basis? What do you mean by simplest basis?
Like what are these elements?
Well, you just have to find any basis, because we know that all the bases have the same number of elements, right? We haven't proved that, but that's something that I said at the start of today's lecture. If you've got a finite dimensional vector space or a finite dimensional subspace, all the bases have the same number of elements. You can work with one of them, and if you will find one that works, you're done.
Yes, like how does that how does that linear combination of this degree 2 or less and then degree 3 like in R3 will be a plane or like a weird shape thing?
Speak to me afterwards about the relationship. I mean, I don't want to get too sidetracked now. Okay. Any other questions? No, right. So let's keep going. Let's keep going on like this. So next example. So we've got here a question where we need to find the dimension of this subspace, and S is equal to all the vectors in R3 x, y, z that satisfy the relationship x minus 2y plus 5z is equal to 0. We know what this is geometrically, right? We know that x minus 2y plus 5z is equal to 0. That's the equation of a plane. So this is a plane. So what we want to do is we want to, I'm going to say that what we know is that we want to show that this is a two-dimensional subspace, right? It makes sense that a plane is two-dimensional. So what we have to do here is you've got to find a basis of two elements. You've got to show that this really is a basis. You've got to show that these two elements are linearly independent, but these two elements are sufficient to generate everything in this form. All right. So take 3 or 4 minutes to do that, and then I'll start writing again. let's do this. Right? Let's do this. Oh dear, where have I put my... Okay. Right, now let's do this. Okay, so we're going to find the dimension of this subspace, which is the plane. The first thing that I'm going to do is I'm going to take what is currently the Cartesian equation of the plane and I'm going to rewrite it in vector form. Right? It's much nicer working with this in vector form. So you can think of this as being an augmented matrix like that, right? So I've got one pivot over here, and I've got two free variables. So I'm going to say, let y be equal to alpha, let z be equal to beta, so that s over there, s is equal to, so if y is equal to alpha, then x will be something like that, and if z is equal to beta, then that'll be minus 5. Okay, so we rewrite this plane in vector form, and once you've rewritten the plane in vector form, we can now make a pretty educated guess for what we would like our basis to be. We're just going to take our basis to be a set of two vectors. We'll consider this set over here B. Consider that set over there B. The 2, 1, 0 and minus 5, 0, 1. Okay. So let's just see what is the set which is generated by B. So the set which is generated by B is the set of all linear combinations of these two things. So it's alpha times by 2, 1, 0 plus beta times by minus 5, 0, 1. And alpha, beta are real numbers. And hold on, that looks really familiar. That is just our plane. Right? Okay, so pretty obviously B is going to generate the whole subspace and nothing but the subspace. And then the next thing we want to do is we want to check whether or not that is a linearly independent set. So you would write down something like this. You write down 2, 1, 0, minus 5, 0, 1, 0, 0, 0. And you do your Gauss reduction. I'll skip over the details. But you Gauss reduce it and you get this far over here. And at this point you can see that the only solution to alpha times by 2, 1, 0 plus beta times by minus 5, 0, 1 equals 0 is that alpha is equal to beta is equal to 0. So only solution implies that the only solution to alpha 2, 1, 0 plus beta minus 5, 0, 1 equals the 0 vector is alpha is equal to beta is equal to 0. So B is linearly independent. We've got that B is linearly independent. We've got that B generates this plane. So B is a basis. B is a basis for S. S has dimension 2. Is everyone happy over here? Are there any questions about this? Yes.
What is the third rule, the
This.
Yeah.
Well, this is just saying that 0 alpha plus 0 beta is equal to 0, which doesn't give you any additional information. So if you wanted to, you could delete that row. You can just ignore it. Any other questions? Okay, so let's keep going then. We've got 15 minutes, which is probably just going to be enough for fact 119, which is very important. And we'll do an explanation, and I hope we'll get through the whole explanation. If we don't get through the whole explanation, you'll have to read up in the notes. Okay. Okay, so this is what fact 1.19 says. Let V be a vector space. Let V be an n-dimensional vector space, right? And then these two statements that I've headed with dots are completely equivalent to each other. One is the contrapositive of the other. If you've got a subset, if you've got a subset S of V, and S has more elements in it than the dimension of V, then S is linearly dependent. Okay, so if you are in R3, and you've got a subset of R3 which has got 4 elements in it, or 7 elements, or 100 elements, you know without doing any calculations, you know immediately that it is a linearly dependent set. If you've got more elements in your subset than the dimension, than the size of the vector space, then we have a linearly dependent set. The other way of writing this down is to say that if you've got a subset T, which is linearly independent inside your vector space V, then the number of elements inside T must be less than or equal to the dimension of the vector space. So if you have R3, and I tell you that your set T is linearly independent in R3, you know immediately it has either 3, 2, 1 elements in it, right? You can't have a linearly independent set which is got more elements than the size, than the dimension of the vector space. In some way, you just sort of run out of space. If you keep adding vectors into a set, you sort of run out of space to make them linearly independent of each other. So if you're working in R3, you take your first vector, which is just a straight line like this. And then you can take your second vector and you want to add it in a way which is linearly independent of the first. So you put it in like this. And you've got a vector here and you've got a vector here, so they together make a plane. And then you take a third vector in R3 and you add it in and you put it sort of normal to the plane. 1, 2, 3. And now if you've got a fourth vector that you somehow want to squeeze in, which is not a linear combination of the other three, you can't do it. You run out of space. There's no way to hide it where it can't be reached by the first three vectors. Okay? So this is just telling you basically there's a bound on how many vectors you can have in a linearly independent set. And that bound is the dimension of the vector space. And let's try to explain why. And like I said, these two statements are completely equivalent, so I'm going to explain the second one. We're going to show that if a set is linearly independent, then it must have fewer elements, or maybe equal number of elements as the dimension. So we do the following. So let V be an n-dimensional vector space. Let V be an n-dimensional vector space, and B, I'm going to actually just give it a subscript over here, B0, and B0 be a basis for V. We've got an n-dimensional vector space, and we have a basis, B0. I'm going to write down B0. B0 is equal to B1, B2, and B, what index goes here? How many entries are there in B0? N, right? This must be all the way up to Bn, right? It's a basis, so it must have the number of entries in which matches the dimension of this space. Okay. We also know, because it's a basis, that B1, B2, all the way up to Bn, they're linearly independent. And since it's a basis, we have any vector in V could be written as a linear combination of the vectors in B0. Okay, so that's what it means for it to be a basis. Now we're going to take an arbitrary set, T. All we know about the set T is it's linearly independent. We don't know how many elements are in it. We don't know what these elements are. We just know that it's linearly independent. So let T, and we can say this is T1, T2, up to T, I think I called it J. Yeah, Tj be a linearly independent set. Yes? What is the difference between dimensions and elements? For any subset, you can ask about how many elements there are in this subset. If the subset that you're asking about is a basis, then the answer to the question, how many elements are in here, is the dimension of the space. Okay. So the dimension is just the count of the number of elements for certain subsets. Okay. So T over here is a linearly independent set. And the idea now is that we're going to, one by one, take an element of T, add it to our basis, and then subtract something from the basis, and it will still be a basis. And we're going to keep doing this. And what we'll see is that we run out of elements in T that we're adding before we run out of elements in B that we're subtracting, which means that there must have been fewer elements in T than there were in B. So that's the basic idea. And let's slowly start doing that. Okay. So we create a new basis, or rather a new set, which will eventually will turn into a basis. Create a new set. I'm going to just call this B1 with a little twiddle. Things with a twiddle on them are not going to be bases. Things without twiddles are bases. That's just a notation that we're going to use to try to keep ourselves clear. So B1 twiddle, T1, B1, Bn. Okay, so we've just added the first element of T into B0. Now what we're going to do is we're going to try to subtract one of these b's in such a way that after we've done that subtraction, after we've removed it from the set, we end up with a basis. So we can't just arbitrarily yank something out. We've got to think a little bit about which one of these we can pull out. We know the following. Since B0 was a basis, B0 was a basis, we can write T1 as this linear combination here. Okay, why is that true? Why does B0 being a basis mean we can do this?
Because at the end of the day, B0 can generate the whole space.
Exactly. We know that B0 must generate the whole space, so in particular it must be able to generate T1. That's the first thing. We know that we can write down this linear combination over here. We also know that there's at least one coefficient alpha p which is not equal to 0. Why do we know this? What's not dependent?
B1.
No.
We don't specify that T is part of the vector space V.
Sure, but that's not enough to draw this conclusion.
No, I'm just saying we didn't specify that.
Oh, didn't we? Okay, we should have. So hold on, we should have said here, let T be a linear. Okay, we should write here T is a subset of V. There. So why is it that alpha p is not equal to 0?
Sorry. Didn't you say that T is independent?
Okay, T is independent, so
Then obviously the alpha
should be 0. No, okay, so if T was, I think you're confusing this with if I'd written down something like this, if I'd written down alpha 1 T1 plus alpha j Tj equal to 0, then because that big set T is independent, all of those alphas would have to be 0. This is a different combination that we're writing down here. We're not writing down a combination equal to 0. What happens if all of the alphas are 0? What can we say about T1? T1 is a 0 vector. Is it possible that T1 is the 0 vector?
If T1 was 0 vector, it would be independent.
Yes. If T1 was the 0 vector, then that set T couldn't be a linearly independent set, right? If T1 was a 0 vector, that set T couldn't be a linearly independent set because it would contain the 0 vector, which is impossible. As soon as a set contains the 0 vector, it's linearly dependent. All right. At least one coefficient alpha p is equal to 0. And we say if all alpha I equal to 0, then T1 equals the 0 vector, but this is impossible since t is linearly independent. All alpha I are equal to 0, then t1, yep, but this is impossible. Okay. So at least one coefficient alpha p is not equal to 0. And what that means is I'm just going to now take that sum up there, I'm just going to rearrange it so that BP is the subject of the formula. Right? So you can write BP is equal to T1. Okay, it'll be T1 over 1 over alpha P. T1 minus, and then all these other terms in the sum have to be pushed across like this. And now the sum is over I not equal to P. So we rewrite BP in the following way. And we create a new set B1 by removing this special vector BP from B1 twiddle. So B1 is equal to T1, B1, B2, BP minus 1, BP plus 1, Bn. Well, let's say what we want to show now is that this process of adding T1 to our original basis and then taking this specially selected BP out means that we have still got a basis, right? And this is important because if this is still a basis, then we can just do exactly the same thing again. We'll put T2 in and we'll take something else out. We'll put T3 in and take something else out. And we'll keep doing this in such a way that we can put all the T's in here without running out of B's to pull out. Okay, so we've run out of time. I'm not going to finish this. I'm going to tell you to do it yourselves, and it will be very hard. But I can also tell you that if you go back and you look at the tests and the exams last year and the year before and so on, you will see that one of the things that we ask you to do in the tests and the exams is to read through proofs and answer questions about the proofs, right? So go and look at the proof in the set of printed notes, read through it. There are actually some questions in the margin about the sort of things you might want to fill in for yourself. And make sure you understand it. And if you can work through it and you can understand it, then probably you can understand the comprehension questions that you're going to get in the tests and the exams.